Hello everyone, my name is Dr. Rajat Dandekar, and today I am very excited to speak with all of you about this topic called OpenClaw RL. To begin with, we will first discuss about OpenClaw. I am sure many of you might have heard about OpenClaw or might already be using some of the features of OpenClaw. If you look at the repository of OpenClaw, it has around 2 lakh 40 stars. Yesterday I looked at it, it was 2 lakh 38,000. So it is gaining popularity at a very rapid pace. In the AI domain, this is almost equivalent to the fame which ChatGPT received in 2022. And one consequence of this is that it has brought AI agents to a much broader community outside people who constantly work in the AI domain. Everyone is now understanding the effectiveness of using AI agents to tremendously improve their productivity and optimize their workflows. So, what is OpenClaw and why did it become so famous? Well, the first thing is that it is a personal AI assistant. And as the word implies, it's an AI assistant, which means it can do jobs and tasks for you. Now, what are these jobs and tasks? Well, OpenClaw sits on top of your applications like WhatsApp, Slack, email, etc., and can interact with people on your behalf. It can tremendously help you boost your communication workflow. Now, the natural question that comes to mind is that these assistants were existing before also, right? We had chatbots. So, what is so special about OpenClaw? The special thing is that OpenClaw actually understands what you want and it actually works. This is something you and I realized. AI agents were popular even in the year of 2025. But the main difference was that these agents used to hallucinate. They used to give answers which were not quite up to the mark. So there was always this feeling that you need a human in the loop. You can't have an AI as your assistant who can reply to people, who can email people, because people will catch that and it won't sound very authentic. Now, OpenClaw solved this problem, and the way they solved it is that they curated this assistant in a way which is almost feels real, and the conversations feel human like. So these can be the applications with which you can integrate OpenClaw can be Slack, it can be WhatsApp, email, calendar. There are a lot of things people can do. People also have started running businesses using OpenClaw as the main agent. Now, this tutorial is not going to be about OpenClaw, how to install OpenClaw, how to use it. There are tons of resources out there. What we are going to be discussing is something very interesting and unique. Uh, if you look at OpenClaw, if you have used it or even heard about it, you would know that it is an assistant which works with any of the communication channels. But now ask yourself the question, let's say you install OpenClaw with WhatsApp. Okay, and every day you're having conversations with it, every day you're interacting with your AI agents. And the question which I want to ask is the agent improving with time? So, is the agent listening to your conversations, understanding them, taking the feedback, and improving itself? Now, if you look at the OpenClaw architecture, you would know that they have done some things to enable it, and those things are called as memory. They have enabled something called short term and long term memory, which takes into account user preferences. They also have a file which is called as soul.md, where you can actually write down how you want the chatbot to behave. Do you want it to be very assertive? Do you want it to be very business oriented to drive revenues, etc.? You can define the soul of the chatbot in the soul.md file, and these things do help in certain amount of personalization. But this main question does not get addressed. You have a lot of conversations with OpenClaw every day, and it does not really improve with the conversations. It doesn't take all your conversations into account. Let's say you ask it to give you a code file in JavaScript, and let's say it gives you a code file in Python instead, and then you tell, no, this is not what I want this. Now this is a one time interaction, but it should somehow improve the model, it should improve your agent, and next time it should not make the same mistake. So this is something which is currently not happening. The agent doesn't really improve with time based on all the conversations that you're having with it. Imagine that you have a friend who is sitting next to you, doing all your tasks for you, maintaining your calendar, replying to emails, replying on WhatsApp, and you have given a file to that person to read, where you say that, look, these are my preferences which are written in the file, act according to it. But you realize that this friend is making a lot of mistakes, so you would like to talk with the friend, tell him that, hey, this is not what I want, you should not do it next time, make this change, right? So ideally you want to influence the brain of this friend. But in OpenClaw, if you try to decompose what OpenClaw consists of, the brain of OpenClaw, where it derives its knowledge and responses from, it is an LLM, which is a large language model, which can either be, let's say, Claude, GPT, etc. Now, all of these users which are using OpenClaw, the brain of OpenClaw is exactly the same. If let's say 1,000 people are using OpenClaw, or 1,000 people are using Claude, let's say, then all these 1,000 people would get their would get their requests directed to Claude, and then whatever answers are coming back from Claude would be received on the user side. So this is the brain, which is the LLM itself, which OpenClaw uses. Now the interesting thing is that the brain remains as it is. We are not rewiring the brain in any way. What we are doing is that what makes user 1 separate from user 2 are these memory and soul.md files, which captures the context. So if you think about it in this way, let's consider two users, user 1 and user 2, and both are using OpenClaw. Now the main brain, let's say, is Claude, and the same is true for user 2 as well. For user 2 also, the brain is Claude. What is different is the context. Every user has different type of conversations with OpenClaw, so the context is different, and OpenClaw creates memories based on this context. And apart from the context, they have implemented a soul.md, which is also different for every user, because you can customize the way you want OpenClaw to respond. But the interesting thing is that this brain is the same. So millions of users using Claude with OpenClaw will be using the same brain. The only thing which is different is the context and the soul. So there is some amount of personalization, but there is a limit to it. You are not really rewiring the brain of your friend who is your assistant. which ideally, if that happens, you would know that this person will never make the same mistake again which it did. So what we want to do is, in this whole tutorial, we are going to be we want to build agents which behave according to your preferences and learn from the conversations that you are having with the agent. So this is where we want to go. We want to build this, and let's make a small connection from OpenClaw to this now. So we want to modify OpenClaw, and the way we want to modify it is such that we want to tweak it in such a way that it learns from the conversations and improves with time. Now the question is, how is this modification going to be done? So if you look at the field of aligning behavior of models to human preferences, the first thing that might strike to you is when ChatGPT was developed, and it became the sensation in December 2022. The first thing I remember is that it felt so human like. It's almost as if I'm speaking with a human. And the reason it felt like that is because it was aligned with human preferences. And the way they had done that was they had used a technique called reinforcement learning through human feedback. So, reinforcement learning has always been the method whenever you want to align a model to human preferences. Now, what ChatGPT did was that, or what OpenAI did rather, was they hired a lot of people who can annotate your data or give preferences that I like this, I don't like this, I like this response, I don't like this response. And the model was fed uh, all those labels, and the model learned from it. This is how the version of ChatGPT that became public first, it felt so human because it learned from all these labels which were given by human labelers. So now we know that reinforcement learning is the method which is used for this alignment. And this gives me a great chance to explain to everyone how reinforcement learning works, and how we can use it to tweak OpenClaw and make it aligned with our preferences. Many people think of RL as a theoretical field, but through this example, I hope I am able to convey the point that reinforcement learning is actually very practical if you implement it the right way, and the algorithms make a lot of sense. So, what we are going to do is that we are going to use the path of RL. So, this question mark that I have put here, it will be replaced with reinforcement learning. So, that is going to be our objective for today's tutorial. We are going to change the open clause behavior so that it learns from every single conversation that we have with it, and it aligns its responses based on the feedback which it is getting on those conversations. The way I'm going to be teaching this is that, so let's make a box which says about the teaching style. I will be dividing this lecture into four parts. The first part is going to talk about F, which is fundamentals. In this part, I will explain about how we are going to think about this architecture, how we are going to implement reinforcement learning. We will look at the basics of RL. I will keep this part very non-mathematical, and I will implement one algorithm which is called as GRPO. We are going to look at one single framework today which can help us align or tweak OpenClaw to align with what we want as a user. This is what makes a human that specific human. If the same brain is used to serve all customers, we are not really leveraging the true power of artificial intelligence. So, this we'll cover in the fundamental section. In the practical section, we will go through some hands on Google Colab notebooks where we will implement what we learned in the fundamental section. So, there will be a connection from F to P. Then is the R, which is the research. In this, we'll consider a real life case study where we will implement our learnings and we will understand how to implement this alignment in a real life scenario. So P and R are linked very close to each other. Actually, F and R are also linked. So I'll draw an arrow from F to R as well. And the last one, which is very interesting, is an end-to-end deployment on OpenClaw. Whatever we'll be learning in the FPR, we'll actually deploy it, and we will tweak an OpenClaw agent which is interacting with WhatsApp, and it's learning from the feedback that you give through WhatsApp and fine tuning itself. So we'll do OpenClaw plus WhatsApp agent and we'll deploy it. The reason I'm taking this approach and not directly explaining to you this last point is I want everyone to really understand what we are doing here so that the fear of reinforcement learning is not there anymore. I really believe the field of RL is so interesting that everyone start should get started with it without worrying too much about the mathematics of the algorithms, the gradients, and everything. It's really very intuitive, and the reason it is intuitive is because it is very closely linked to the way humans think. Out of all ML algorithms, supervised learning, unsupervised learning, RL is the one which is closest to us because I think it mimics something which happened in human evolution, and that something is the ability to improve and learn from trial and error. Whenever we are learning to ride a bike, we fall and we get hurt, but later we don't make the same mistake again. We improve from it, we learn from feedback. At the heart of it, that is all there is to reinforcement learning. Underneath all these fancy mathematical equations, this is exactly what is happening. So I want to explain all of this to you in this whole tutorial which I have designed. Okay, so let's get started with it. We'll first start with the first part of the lecture, which is the fundamentals. I have written an article which I will be using to explain all the different points or concepts which are included in the fundamentals. And whichever concepts which I want to highlight, I will be taking that content and pasting here in my notes so that they remain here for a reference in the future as well. Let's get started with the fundamentals now. Okay, so first, let's begin by understanding what OpenClaw is. As we have discussed, OpenClaw is an AI assistant that lives on your machine. You might have seen people buying in bulk uh, Mac Minis, which is a CPU, which is essentially your entire computer, which you can link with a monitor. And the reason you need only a CPU is because OpenClaw can connect with all these applications which are using the CPU RAM, and these applications can be WhatsApp, Telegram, Slack, Discord. So this is the diagram which shows you which all streams OpenClaw agent can connect to. I have divided it into messaging, system, and services. And today we'll be focusing on one application in messaging, which is WhatsApp. But people are using it for Telegram, Slack, Discord, and you can use it for a range of things. Now, one of the most important things that everyone should understand is that OpenClaw is like uh, it's a middleman between you and the LLM. So first, let's take a screenshot of this to save this diagram on our notes. Okay. Now, what OpenClaw is essentially doing is let's draw three components. Okay, so this is you, this is OpenClaw, and this is the LLM, which is, let's say, Claude or GPT. Now, what happens is that whenever you send a request to OpenClaw, like let's say, message this to my friend in WhatsApp that I am not available today and this is my calendar. What OpenClaw does is it transfers this request to the LLM, and it gets an answer back from the LLM, and then it combines it with the context and whatever it has in the memory, and it just gives you the answer back. So this is the request which you made, which is transferred to the LLM, and this is the response, which is combined with context and everything. Or rather, I think let's put it in this way: the response which you get from the LLM, the response is a combination of your request plus the context is also given back to the LLM. So what the LLM receives is the your request plus the context, and you get a response back which OpenClaw transfers to you. So what this diagram basically depicts is that OpenClaw is using the brain of the LLM itself, and it is using your request, which is going to some server which is sitting in some country. Something is being processed in that server. Some weights are being analyzed, multiplied, added together. You get the answer back, and that answer is given back OpenClaw by OpenClaw to you or on WhatsApp, whichever channel you are using. So the large language model is really at the heart of the entire orchestration which is happening in OpenClaw. Now, what makes OpenClaw so powerful is that it has a lot of things, a lot of integrations, browser control, persistent memory, etc. And all of this works beautifully. That is why it has got so many stars in the first place, because people are actually using it. It really works, as I said before. Now, if you look at the OpenClaw architecture and what it does, there is one fundamental limitation. The language model behind OpenClaw is generic. The same model which OpenClaw is using to serve its clients, it is trained on internet scale data, which is massive amounts of documents, YouTube videos, etc. And the important point is that it does not know your preferences. It does not know what you like, what you don't like, etc. It is too generic. So, the question that we are trying to address in today's tutorial is, can we make OpenClaw learn from you? Can we make it such that it is personalized to what you want, to your tastes, to your likes, to your dislikes? What makes you the person that you are? For example, it OpenClaw currently does not know your coding style, your writing tone, or the way you like the emails drafted. Now, let us take a very concrete example. Suppose you open OpenClaw every day to help you write code, and every single time you tell it, I don't like TypeScript, I want plain JavaScript, and you give it explicit feedback in natural language, maybe through WhatsApp, right? But the next day, it again gives you an answer in TypeScript. So this is familiar because a lot of LLMs do this. They don't remember everything we have said in the past. The reason they don't remember everything is because the context window of the LLM is limited. It doesn't remember everything. Humans also behave in the same way. We have a excellent mechanism to compact all the conversations in our brain so that we only remember the most important information. So this mainly happens because the model is frozen. The model which is sitting on the server, you are not changing the weights of the model. The model is frozen, you are just querying the model and getting the response back. Now imagine an alternative scenario where you have a model which is continuously learning. The model is continuously evolving, it is learning from Your feedback, it is learning from your responses, it is getting better and better with time. Now this is exactly what we want to reach. We want to go from the left diagram to the right diagram. So let me go ahead and add it in my notes. Okay, so we want to go from left to right. We want to develop an assistant which actually improves from our interactions with it. Now, the first thought which might come to your mind is, what if we fine tune the model, the base model directly by collecting all the conversations that we have and then start the fine tuning process? That is an interesting approach, but the drawback of that approach is that you would have to collect the conversations and manually label the training data. You have to stop the model, run a training job, and again restart it. So it is a complex process. Ideally, what you want is, you don't want your workflow to be disturbed in any way. You want to interact with OpenClaw the way you have always been interacting. You want all of it to be taken care of autonomously. You want the model to improve on its own. You don't want to sit down, collect all the data, fine tune the model, wait for the model to improve, then again run your job, etc. That is very time consuming. So, traditional fine tuning is definitely not the approach that we want to take uh, to achieve our objective in this tutorial. What we want is, we want an AI which can continuously improve in the background from natural conversations without us having to do anything special. And this is what brings us to OpenClaw RL. Now, what is OpenClaw RL? Let us see. OpenClaw RL is a repository which was released almost 2 days back, and it has gathered more than 400 stars right now. It is a repository which has shown for the first time that we can personalize OpenClaw and tailor it to our own tastes and our own preferences. So, it is a reinforcement learning framework that wraps our OpenClaw agent and turns everyday conversations into training signals so that the model literally gets better the more you use it. We are going to refer to the architecture in OpenClaw RL to learn how it works and what are the different components which are used in the architecture. And we are going to try to understand and even implement it from scratch on our own. Okay, so now let us go ahead and actually understand the different components which have been implemented in OpenClaw RL. Okay, so the architecture that we are going to understand has four different components, and we are going to understand it on a very fundamental level because it is going to take a shift from understanding what it means to simply prompt an LLM and get an answer back to something where we actually want to fine tune an LLM using reinforcement learning. Okay, so let us understand this in this segment, which we will call the four components of OpenClaw RL. Okay, so the first component is the agent itself. Okay, so now what is the agent? The agent is nothing but the large language model which OpenClaw is using. Just go back to this diagram where we understood that OpenClaw is using a LLM as its brain. Okay, so there is always an LLM at the heart of any AI agent. which is what we are talking about here. So this I'm going to call LLM, which is, let's say, Claude. Or let's take an example of another LLM which is more accessible, which is Quen, let's say. So let us say that this is our agent, which is this is the LLM which our agent is using to give us the answers that we expect it to give. Okay. Now, in this framework, one of the major differences from how people generally use OpenClaw is this agent is usually residing on some server. For example, if you are using Claude, then the LLM is residing on a server which is purchased by Anthropic somewhere in the world. If you are using GPT, then the LLM is hosted on some server which is purchased by OpenAI, and you do not care about where the server is hosted, where the server is located. You do not care about the infrastructure. But in this case, we have to care about the infrastructure because we are going to be hosting the agent ourselves. We are going to be hosting the LLM on our infrastructure. Now let's try to understand what this means. Okay, so there are two different options here. The first option is where this is the server, which you have no idea where this server is sitting. Let's say you're using a Claude model, and you are making a request to this server, or rather OpenClaw is making a request on your behalf, and you are getting an answer back from the server. Okay, so this is scenario 1, which is how most of the people in the world, 99% of the people, are using OpenClaw. They don't care about where the server is hosted, they don't care about the infra at all. Now the second case is very similar to this. The diagram remains similar. The only thing which changes is here we have to your own infra, and by infra I mean your own GPUs. So this is the second case. Now the reason why we use this second case is, at the end of it, this is the brain. Now when your brain is sitting in some server, you do not have access to control the brain. You can ask the brain some questions, the brain will give you some answers back, but at the heart of it, you cannot rewire this brain. But since your brain is now sitting on a server which you control, you have access to every single weights in the neural network of that brain, which means that you can tweak every single weight in the neural network, which means that you have the power to rewire the brain. So here you can rewire the brain, which is exactly what we want. We want to actually make the agent improve with our conversations, right? So we should have control over the agent. We should have access to the agent's weights. We should know the values of the weights. So it should be an open source model. And we should also have the capacity to modify these weights. That is what we want. That is why we are going to host this agent or the LLM on our own infrastructure. This is the most important point which we have to understand at the beginning of this tutorial, that if we want to implement this, then we would have to think about renting GPUs, downloading models from wherever they are available, and then uploading them on our GPUs. Okay, so this is the first component of the framework, which is the agent. Now, this component is there for OpenClaw also without RL, but the only thing is where this agent resides, where does the brain reside? in one case the brain is locked in a glass container which you cannot access. In second case the container is open, you can go ahead, you can put a wire inside and you can change and tweak around the brain. That's the main difference between the two methods. Okay, so this is the first component, which is the LLM itself, which is what is mentioned here as agent serving. This is the model that you talk to. It wraps your hosted LLM as a API and serves you requests in real time. Okay, now the second component, which is called as rollout collection. So this might be a new word for all of you. The meaning of rollouts. Now, rollout is nothing but when you prompt an LLM, the answer you get back from the LLM, that is called as one single rollout. Now, what does this collection mean? Here also we'll take an example. Let's say you are a user and this is WhatsApp. Okay, so now let's say this is CloudBot. Let's mark it in green. This is not very visible. Let's make it dark. Okay, so this is your conversations with CloudBot. Let's say in one session, and this one is you. Let's say you are interacting with OpenClaw. I keep switching to CloudBot because the name has been changing since the time they launched. So this is OpenClaw, and this is you. This is OpenClaw. This is you. Okay, so these are the bunch of conversations which you are having with OpenClaw. Now, what happens in the rollout collection is you want to collect data which you want to use to improve the model, right? Now, this data is going to be in a format which looks like this. The data is going to have two columns. The first column is the conversations, and the second column is how much you are going to rate that conversation. So we are going to be worrying about the second part a bit later. A bit later. For now, let us just focus on the first part, which is the conversations. This is very similar to in supervised machine learning. All of you have probably seen this. The example which people start out with is houses, area of houses and their prices. So this is the area, this is the price. So you have an area of 200 square feet. The price is $5,000. You have an area of 300 square feet. The price is, let's say, $7,500. And you have a lot of data like this, and you use this data to train your regression model. Now here also we want to construct a data set because we want to use this data set to improve the LLM which we have hosted on our own servers. Okay, so now the conversation data that is used is typically one single turn. So this is called as one turn, where the agent is speaking and you are speaking back to the agent. Sometimes you can take multiple turns as the data set. So you collect a lot of these conversations. So this becomes the first side of your data set, which is the multi-turn conversations which you are having with OpenClaw. Now, the way that the rollout collection is deployed in this repository is that they collect 32 conversations at one time to fine tune the data. So this is the rollout collection. Let's say you're having conversations on WhatsApp with OpenClaw, and you're interacting with it, you ask a lot of questions. Sometimes you're happy, you say great answer, sometimes you say not very good answer, I don't like this, improve it. There is an agent which is running in the background, which is collecting all this information, one single batch at a time. 32, 32, 32, 32. What happens to this batch is something we'll see, but for now we'll just understand that there is something who is monitoring our conversations and collecting 32 at a time in batches. So that is nothing but the second component, which is the rollout collection. It intercepts your live conversations and tracks each conversation as a session, classifies every turn, and identifies which turn can be used for training. Now, the third component is the most important component, in my opinion. So, we will call this a second component. The third component is called as the process reward model. Notice that this is the second model which we are using apart from the LLM which is hosted on our own server. So this is the, I keep saying on our own servers, but sometimes in most of the real life cases you end up renting out GPUs. So what is the process reward model? Just collecting the conversations is not enough, but you need to score every conversation. Let's say here you give a response that this is bad. So you get a score of -1. This conversation gets a score of -1. This, let's say you give a score of good, excellent. This gets a score of +1. Similarly, every single turn in the conversation is scored as +1, -1. This is exactly what ChatGPT did in 2022, but they hired human labelers to do it. Now, here what we are doing is we are using a model to automatically score the conversations. So the PRM is linked here, process reward model, and then every single conversation is stored. Now, this is something which is a major shift from human feedback, because this feedback is not given by any human, but it is given by AI itself. Now, in most of the cases, or and at least in this repository, the model that they use is the same model which is used as the brain. So if I'm using Quen as the brain, I'm using the same Quen model to generate a score for my conversations. Now, how is the score generated? Let's say you design a system prompt where you tell in the system prompt that, hey, look at these conversations, give a score of +1 if the user is overall satisfied. If the user is not satisfied, give a score of -1. Okay, so this is called as a binary reward signal, because you're only giving two signals. You're giving +1 for a good reward, and giving -1 for a negative reward. And why this is called process reward model is because you are giving rewards for every single conversation. So that is why it is called as a process. There is another type of reward model which is called as outcome based reward model, or ORM. Here we are using a PRM, which is a process reward model. It is just a fancy word for a model with a given system prompt who is looking at your conversations and scoring it. You can think about it as a judge. You are speaking with someone, let's say having conversations. Imagine that there is someone constantly sitting on your right with a pen and a paper, looking at your conversation, scoring. Are you happy with the LLM? If yes, high score. If no, -1. And this PRM is again running continuously in the background. The trajectories are collected, then they are scored. 32 trajectories are collected, then they are scored. This process continuously happens as you interact with the agent. So this is component 3. It is a separate model that evaluates how good each of the agent's responses was. It runs asynchronously, does not need to evaluate responses in real time. Okay, so this is where the model, there is another model. Now you can think of your architecture. You already have the LLM, which is the brain. Now, along with the brain, you have a judge also. So let's imagine the glass container where we are hosting our models. So this glass container has two things now. It has the brain and it has the judge. Okay, so now this is what we need to have in our infrastructure when we set it up, right? We need to have the brain, who is which is the agent, which is the heart of this entire personal assistant. We need to have a judge, because the judge is what is capturing our preferences implicitly through our conversations itself. Now the fourth component, after all this happens, you might be thinking, when are we tweaking the brain? We have access to the brain wiring because we are hosting it ourselves, but where are we tweaking it? This is what is happening in the fourth step, which is the training. In the training, what happens is that you collect this data set. So let me copy this. I hope it is copied properly. Yeah, not bad. You collect this data set and you feed it to your brain, and this is where you modify the brain. Now the question is, how do we modify the brain with just conversations and scores? How do we let the brain know that I prefer these conversations, I don't prefer those conversations? That is something where the power and the beauty of reinforcement learning actually comes in. This is exactly where reinforcement learning really shines. And the methods which have been developed in RL decades ago are going to help us uh, complete this modification of the brain. So this is something which happens in the fourth component, which is the training. This is where the learning actually happens. The trainer takes the evaluated samples and updates the model weights using reinforcement learning. When it is ready to push a new set of weights, the serving component pauses, loads the new weights, and resumes. So, to summarize, there are four components. The first is the brain, which is the LLM. Since we want to tweak the brain, uh, this is something we have to host on our own infrastructure. We cannot make an API call to a gated brain, which we have no access to. Then we have to collect responses asynchronously, one by one, how we are interacting with the agent. That is done by a component called as rollout collection. The third is the judge, which is sitting right next to you, scoring your interaction with your agent, and then giving positive scores if you are generally responding well. If you are not responding well, the agent gets a negative score. All this scoring is only useful if we use these scores to fine tune our agent. This is what happens in component 4, which is policy training. All these four components will have to work in synchrony with each other to make sure that our personal assistant is aligned with our preferences. Now let's go back to the top aim which we started out with. We wanted to make a model which continuously improves with time. And now we have tried to set up a pipeline which can collect conversations autonomously and then score those conversations using a judge and learn from it. So this is something which is also called as reinforcement learning through AI feedback, or RLAIF. This is a field of study which has emerged after RLHF, which is reinforcement learning with human feedback, was made popular. Now you might be thinking, okay, how does reinforcement learning actually work, and how do we train our brain to reinforce conversations which have got positive rewards and penalize conversations which have got negative rewards? This is where we are going to understand a bit of reinforcement learning algorithms as we go along. Okay, Fine. So this is the first part of fundamentals. Now we are going to move to the second part of the first fundamentals modules, where we are going to understand about the reinforcement learning algorithm, which is used here, called GRPO, or Group Relative Policy Optimization. This was made popularized by uh, DeepSeek, and it is very intuitive. We are not going to go too much into the mathematics of it, but we are going to understand exactly how it works. Okay, so let us move on. We have covered the four components of the OpenClaw RL architecture, which is the agent, the brain of our architecture. The second is the rollout collection, which is collecting or converting conversations into training signals or training data. Third is the process reward model, which scores the conversations. And the last is the actual training process or tweaking the brain itself. Now, let us focus more closely on the rollout collection. And in particular, we will try to understand how the conversations are converted into training data. Okay, so this is how the rollout collection works. The first is the session aware tracking. Every conversation that you have with OpenClaw is tracked as a session, and this means that every system maintains turn ordering within each session. Now, every turn is not used as a training signal. It is divided into mainline turns and side turns. Okay, so mainline turns is the core interaction turns where the agent actually generates a response and the user provides a feedback. Only those type of conversations are used as the training data. Then the second type is side turns, where we have system messages or other turns which do not carry any useful signal. Those are not used for training data. So it is important to look at the conversations and divide it into these two types, so that you only include data which is relevant and it contains most of the training signal. Okay, so let's try to understand this with an example. Let's say the user says, write me a Python function to sort a list, and you get a response back from the agent which says that, okay, here is a JavaScript function. Now, the next state signal is what provides the user feedback. For example, after the agent types this, the next signal that you say is, no, I said Python, not JavaScript. Now, these three blocks, which is the first user cell plus the second agent plus the third, that constitutes one training conversation. Similarly, next, the agent corrects itself and the user gives the feedback in the next state signal. So these two combined become another training data set or another data point in the data set. So this conversation, which I'm just showing right now, it has two data points which correctly include the agent response plus a feedback from the user, which constitute to be a training signal. So when the agent responded with JavaScript 2, the user corrected it with, no, I said Python. This correction is the negative feedback signal for turn 2. Similarly, when the agent fixed its response, the user said perfect, thanks. This is the positive feedback signal for turn 4. Now, here it is important to understand that no manual labeling is needed here. Okay, so the conversation itself becomes a training signal, which is quite unique. Remember, I said when ChatGPT was released, human labelers actually sat down and gave uh, scores by themselves. This is very different. This is where we are automatically converting conversations into training data. Okay, so now what we are going to do is we are going to actually look at implementation of this. So here we have a very nice Google Colab notebook, which if you open, you will be taken to this notebook here. and it contains a lot of to do exercises as well. Here I have already implemented those exercises, but all of you can try it out on your own because you will get practice on how to implement these intricacies in the architecture on your own. So we are diving a little bit deeper into how the conversation is converted into a training signal. And this is where this Google Colab notebook is going to be very useful for us. So now if we go back to our notes, we have come to the second part of this tutorial, which is the practicals. The practicals is very closely linked to the fundamentals, and in fact we are still going through the fundamentals, but for one section in the fundamentals we have moved on to the practicals because we want to actually implement it out on our own and see how it works. Okay, so what we are going to understand is how are user conversations converted to training data. Okay, so this is going to be our aim. I will give a link to this pod's website, and all of you should open this and try it out as I am explaining the different cells and how they work. So we have added this narration also here, where this narration is specifically intended to keep you hooked onto the Google Colab notebooks. Many times, what happens is that students are going through the notebooks by themselves, but they do not have any proper narration, so they get lost in the notebook. So this narration is intended to keep your motivation up while you're going through the different cells in the Colab notebook. Additionally, we have also added this AI assistant, which you can chat with if you have any doubts in the Google Colab notebook itself. So this assistant has been trained on this specific notebook, so it can help you answer a lot of your questions. And now this is the part where you actually develop a lot of confidence that you don't just know things at a surface level, but you can actually dig deeper and try to understand some of the deeper things on how these things actually work. Okay, so let me run the first cell, which is setting up Python, PyTorch, etc. And let's understand the notebook also involves a lot of text so that you have some guided material which you can use. Okay, so in this notebook, we will build the rollout collection system from scratch, the component which transforms our everyday conversations into a structured training data. And we are going to look at four different things. First is how to track multi turn conversation sessions, and how to classify each turn as whether this turn is trainable, this is not trainable, how to extract next state signals where the user's next message becomes the feedback for the model's previous response. This is something which we have looked at here. This is the next state signal because it is a feedback to the model's previous response. So how to extract that, and how to produce ready to train samples with this triples prompt, uh, response, and the feedback. This is something which we have vaguely written down here. This is the prompt, response, and the feedback. So we are going to understand how that is set up. So this is what we are going to build. We are going to extract the conversations, which is, let's say this is one single conversation, and out of this, the response. This is the response of the user, and this is the feedback. So this is negative, and here the response of the user is so this is a condensed response. We'll see the actual response. The feedback is perfect thanks, which is a positive response. So you can see this conversation has been converted to this. One conversation has been converted to two training samples where we are storing the feedback along with the response from the user. So here the response is JS sort, here's JavaScript, and the feedback is so this is the response from the agent actually, and this is the feedback from the user. So you put that in a conversation and you give a negative score to it. Similarly, for the next three user assistant interactions, uh, where the response is sorry, here's the Python version. So here the response is actually short. This should be the actual response, and the content is perfect thanks. So this is what we are going to do. We are going to convert a conversation into prompt, response, and feedback training samples. Okay, so let us think about what happens in a typical conversation with an AI assistant. You ask something, the model responds, and then you react to that response. The reaction is very informative, like, great, exactly what I needed. So this is a positive signal. Then the reaction can be, no, I meant the other thing. This is a negative signal. Then the response can be, can you also add error handling? This is a mildly positive. Then this is that code has bug on line 3. This is a negative signal. So this is the next state signal idea. What this means is, in traditional reinforcement learning, there is a separate reward model which is associated, which tells the agent how well the agent actually did. Imagine you are learning to ride a bicycle, right? So you fall down and you get a reward from the environment that I have got hurt right now. So this is something I should not do. Now, in many RL problems people have tackled in literature, they write down a separate reward function. Now here the unique part of the process is that the reward is, we don't need a separate reward function for this because the reward is already implicit. The user is already telling you the reward. So it only makes sense to capture that reward, right? The reward is implicit in the conversation. But not every message is in a conversation is useful for training. Some might be system messages, the user asking for a clarification, etc. Okay, so now before we start the notebook, one simple question for all of you is, in a 10 turn conversation, how many training samples do you think we can extract? Is it 10? Is it 5? Is it just one? Remember, one training sample should have the next state signal also, which is the response from the user. Okay, so just a little bit of uh, mathematics here, which is just a notation. A conversation session is a sequence of turns where here you see we have used a symbol of R and M, where R is the user's message, then what the assistant types, and this is the system prompt. Okay, and M is the content of the message. So a turn RT is trainable if R is an assistant, which is the model has actually produced a response. Then there exists a subsequent user return, and the user return is a reaction to the assistant's response. So basically, the training sample will be the context, the response, and the feedback. Um, just to summarize what we are saying here, we are going to denote something as a training signal if we have a message from the assistant if the assistant is actually saying something, so by assistant I mean agent, and we have a user response to what the assistant is saying. If we have a user response to what the assistant is saying, then this combination is what we are going to look for in the training signal. So if we have an assistant saying something but the user did not say anything back to it, which is, or user says something which is totally unrelated, then that is not going to be included in the training signal. So we will also look at an example to understand this better. Okay, fine. So we are denoting the turns or the roles into three types: the user, which is the person interacting with the agent; the assistant, which is the agent itself; and the system is like a system prompt. And we are going to classify the turns into two types. One is the mainline turn, which is the main turn which we are going to classify. Remember, we have discussed that here. This is the core interaction, and the second is a side turn, which is non-trainable. So that is important for us. Let us look at a sample conversation. Okay, so this conversation has how many turns? One, two, three, four, five, six, seven, eight. So this is a 8 turn conversation. The first role is system, because I am giving a system prompt. You are a helpful coding assistant. Then the user says, write me a function. The agent writes a function. The user says, no, I said Python, not JavaScript. Then the assistant again says something. The user says, perfect, thanks. Then the user also asks this. Assistant says something. User says something back. Now, one question that all of you can think of is, in this sample conversation, based on this definition of a training signal, how many training signals can you extract? It is definitely not 8, it is less than 8, right? Because you need a, a user response and an assistant response both in a training signal. So this conversation has 8 turns. Now we are going to classify every turn into mainline or side, and we are going to take an example for that. Maybe I have not run this cell. Let me run it. Yeah. Okay. So with the 8 turns which we looked at, the first is definitely a side turn, because it is something which is a system prompt, and all others are main turns, because either the user is responding or the assistant is responding. So you can actually visualize this very nicely in this graph. So you can see the first is marked in gray because it is a side turn. It is not something which the user or assistant is talking about. But this clearly shows the first step is to divide a conversation into a bunch of turns, and then subdivide it into a main turn and a side turn. Now you only look at the turns which are the main turns. Okay, now for every assistant's response, we extract the next state signal, which is the user's next message that serves as a natural feedback. So this is very important. Here, if you look at it, we have extracted, this is the first feedback. So for every assistant response, the first assistant response is, here is a sorting function. This is the next state signal that, no, I said Python, not JavaScript. Then the feedback, then the assistant improves, and the feedback to that is, okay, great, this is Python, so I like it. Then the user asks another question, and then assistant responds to it. So you get 3 pairs, right? So probably there are 3 samples in this 8 turn conversation. 3 pairs which we have extracted. Pair 3 negative, pair 1 negative signal, pair 2 positive, and pair 3 positive signal. Okay, now the next step is to do. I have already filled it here, but all of you, when you open your Google Colab notebooks, you will be able to interact with it on your own. So this is where you build your context assembler, and you implement the complete rollout collector. So we already know that there are three samples here because we have looked at these three pairs. And this is what the rollout collector does. You give it any conversation, it will convert that into training samples by first classifying the main turns, then identifying the next state signals, and then dividing that into the samples. So you put all this together, and you see there are three sessions here, and you can immediately tell that okay, in this session ignore this because this is a side turn. This is one sample, this is the second sample. Wait, is this this is one sample actually, and then this is the second sample. So there are two samples in this session. Let's see if it's getting, yeah, two samples and three samples. So let's look at this second session. Here we have user asking something, assistant saying something, and great analogy. This is the first sample, and then this is the second sample. Okay, fine. So we have two samples in that, and the last one probably has user assistant three times, so there would be three samples. So that makes sense. And analyze the distribution of feedback signals in our training data, and we can plot it. So you can see that we have three samples in the first session. We have two samples in the first, two in the second, and three in the third. And here you see the number of positive samples is 5, the number of negative samples is 2, and neutral is 0. We can also visualize the next state signal flow. Now here we can clearly see that in the first session, right, these are the two samples, and this is the next state signal which is marked in green. Next state signal is nothing but the feedback given by the user, so you can clearly see the next state signals over here, and green is the positive, and red is negative. Now the last thing is you convert that to JSON file for the training data. So this is what it looks like as a sample record. Session 1, responses 2, feedback 3, and this is the first sample from the session where you are saying this is the system prompt, and the user asks what is the capital of France, and the response is capital of France is Paris, and the feedback is correct. So remember, we started out with we need to have training sample which consists of a prompt, a response, and also the feedback. So this is the prompt, this is the response, and this is the feedback. So this is one training sample from the first session. Now this session we know has two training samples, but we are only showing here one for the record. If you do one here, I think you should get the second one. Yeah, so this is the second one which has been written over here. Okay, so this is great. And OpenClaw RL also guarantees that every session contributes at least one training sample. So this is again, which you can summarize here. The pipeline is we first identify the turns from the raw conversation, which is the main turn, which is the side turn. Then we extract the next state signal, which is the feedback from the user, collect a bunch of training samples, and convert that into a logging data. So we have 7 training samples from the 3 sessions, and the average is 2.3 samples per session. So every session should have more than at least one sample, which is kind of makes sense. So now every conversation with your AI now generates training data. So let's go back to the first objective that we started out with. Remember, we had to create an agent which behave according to your preferences. So to allow an agent to behave to your preferences, we should first capture the preferences, right? And this is exactly what we have done in this first practical session, where we looked at how to convert the conversations into training data, or training signal rather. Okay, all of you go ahead and run this Google Colab notebook, and next we'll come to the most important part of today's tutorial, which is the training algorithm itself. So the algorithm that we are going to discuss today is called as group relative policy optimization, or GRPO. So if you look at this paper, the GRPO algorithm was introduced by DeepSeek team in 2024. So here they quietly say in the last three lines, secondly, we introduced GRPO. And this algorithm has really blown up. The number of reinforcement learning papers which use the GRPO algorithm is a lot. And there is a specific reason why GRPO has emerged as a very popular algorithm, uh, in spite of it being a late release in 2024 almost, and 2025. So in this particular project, we are going to be using the GRPO architecture. So now let's again go back to the fundamentals. We keep switching between fundamentals and practicals, but that keeps our motivations maintained as we understand this project. So we are going to understand GRPO, and before we understand GRPO, we need to understand the purpose of this algorithm and what exactly are we doing over here. Okay, so right now what we have seen is we have collected some training data, right? Where and there are a bunch of conversations here, and there is a score here. Okay, so now the question is, this is fine, we have this conversation score data, but we have a brain sitting somewhere that we want to modify. And this challenge we have not addressed so far. We have not addressed how we are going to modify the brain from this conversation score data. And this is exactly the kind of challenge which the process of reinforcement learning is actually trained to do. The algorithm is used to tweak the brains of models so that they are aligned with human preferences. Now let us understand how that happens, okay, and why is that, how does that work. So let's look at a large language model itself, which is an LLM. Now assume that these conversations are named 1, 2, and 3. Okay, now we have three different conversations. What is an LLM? An LLM is a model which generates one token at a time. So if I give this sentence once upon a to the large language model, the model can go in any direction. It has a lot of things to choose from. It has cat, it has temple, it has noon, but we know it's going to select time more often than not. And the reason that is the case is because this pattern it has seen a lot in its vocabulary. So the model is going to predict time as the next best token, or the next token which has the maximum probability. Okay, so now what we want our reinforcement learning algorithm to do basically is, uh, let's say we now have the LLM, which is sitting over here. The LLM is generating four samples. Okay, so this is sample number one, this is sample number two, this is sample number three, and this is sample number four. And I am going to denote these samples by circles. Okay, so there are four different samples which the LLM generates. So we call it S1, S2, S3, and S4. Okay, now what happens is there is a reward model which scores all these different samples, let's say. So we call this as, let's say we use the name process reward model, which we have already looked at before. And the model generates some scores for these four conversations. So let's say uh, I mark these with the red, whichever have got bad rewards. Okay, and let's say the brightest color means it has got the best reward among others. Okay, so now what I want to do is I want my algorithm to sit somewhere over here. I want my algorithm to sit somewhere here, and take all of this as an input. And after this, the algorithm should do something very specific. It should connect to all these paths. Okay, and I'm going to use the word P for penalize. It should penalize S1, S2, S3, and it should reinforce S4. And this information should be fed back to the LLM and updated. So the algorithm should basically say that S1, S2, S3 have bad rewards, penalize them, and increase the probability for generating answer S4 more in the future. Now, this is exactly where the RL piece fits into. There have been algorithms like this proposed before in the literature. The first algorithm which became popular is called as proximal policy optimization. The proximal policy optimization was great, but this entire thing that we saw here, PPO did something interesting. In PPO, you have this LLM, you have a process reward model, but interestingly, you have another model which is called as the critique model. The critique model is used in tandem with the actor model, which is this is also called as the actor model, which is the main agent, and then both of them are used in tandem, so that you are able to communicate to the LLM that produce more answers which are which have higher rewards and penalize answers which have negative rewards. Now what this did was, you see there are three models now loaded into the memory. There is an actor, there is a critique, and there is a process reward model also. So it ends up consuming a lot of RAM. It's extremely memory intensive. And even though PPO was the algorithm which ChatGPT also used, or OpenAI used to fine tune GPT and make it align towards human preferences, but it consumes a lot of memory. What GRPO did was, and the way this critique model, why this was used is, after you generate the rewards, there is a process which is, so I need to move it here. You use the critique model here to calculate something which is called as advantages. Okay, so the you calculate something called as advantages, and these advantages are fed to your algorithm along with these rewards, which is this arrow. So the advantages are fed to the algorithm, and you needed the critique because without the critique you cannot calculate the advantages. Now what is an advantage? An advantage is something which tells the model how better or worse is better or worse the model is compared to the baseline performance. We will understand advantage much better right now, but I'm just giving a brief understanding about it. Now, what GRPO did was, GRPO came along and GRPO said that, hey, this is fine. And why do you need three models here? You can do the same job by just using two models. GRPO completely got rid of the critique model and directly generated the advantages just from the reward signal itself. It said that we don't need a critique model. We can calculate advantages directly from the rewards, and that actually works. People realize this is a very clever trick. This is something which you can easily do, and you can calculate the advantages. Now how are the advantages calculated just from the rewards? So let's copy this block here and try to understand. So let's say these rewards are have a value of 1, 0, 2, and -1. Okay, so how GRPO calculates advantages? GRPO first calculates the mean of all the rewards. Now the mean of these rewards you can calculate, which is 3 minus 1 2 divided by 4, which is in this case it is zero point 0.5. Now what you do is you subtract the mean from all the rewards. You subtract the mean from all the rewards. So basically you subtract 1 minus zero point 0.5, so that becomes zero point 0.5. this becomes minus zero point 0.5, this becomes 1.5, and this becomes minus 1.5. And ideally you also divide by the standard deviation. So these are the ones which are the advantages. Now this is advantage a1, this is advantage a2, this is advantage a3, and this is advantage a4. And all you need in the algorithm is you need to substitute the advantages back into the gradient formula. That's all. So you only need the rewards to calculate the advantages. Now the sign of the advantage clearly tells you something, right? Positive advantage means that it's something which is performing better than the baseline, which makes sense because this value is 1, it is better than the baseline. And you see the completions which have negative advantages, they are performing worse than the baseline, which is this and this. So here I have given this should be plus 2 actually, but let's ignore the oversight. So this is how the advantages are calculated. You just subtract the mean of all the rewards from the rewards itself and then divide it by the standard variation and directly use these advantages in the gradient formula. Now when you implement this in practice, it does not require you to have a separate critique model here, because just from the rewards itself you can calculate the advantages. So let's try to read that again here. In standard RL for language models, an algorithm called PPO is used. PPO training requires a separate critique network, essentially a second neural network that estimates how good each response is. This doubles the memory and the compute requirements. GRPO estimates or eliminates the critique entirely. It samples a group of G responses for the same prompt. In our case, it was 4. Compute a reward for each one, normalizes the rewards to get the advantages. That cuts the memory and compute by nearly 50%. So here if you see, we have taken an example of 4 rewards, plus 1, minus 1, plus 1 and 0. Here also the mean is 2 divided by, or here the mean is minus 1 divided by 4, which is 0.25, and the standard deviation is 0.83. So you subtract this from all these rewards and divide it by the standard deviation, you get all these advantages. Now you see the advantages which are the most negative, they have a negative reward score, and the advantages which are very high, they have positive reward score. Now what our model is designed to do is, the model is designed to reinforce sentences or conversations which have a positive advantage and penalize conversations which have a negative advantage. So R1 and R3 will be reinforced, R2 and R4 will be penalized. Now, where do these rewards come from? We already know that these rewards come from the process reward model, where the process reward model is grading all these samples. Now, one interesting thing is that the process reward model, we already looked at how to create this response and next state pair, right? The PRM grades it multiple times. For example, if you have the agent response, this is the code, and the user message is no, I asked for Python, this is Java. So the reward model evaluates it 3 times and then takes a majority vote. So first time you get a value of plus 1, second time a value of plus 1, and third time a value of 0, and the majority vote is plus 1. So this is just one detailing or intricacy which we should be aware about. The reward model is not like you pass a pair, a training pair, to the reward model and it's directly going to give an answer. We do it 3 times and take the majority. The reason it is done 3 times is because models are somehow flaky sometimes, they can hallucinate. But if you do it multiple times, you know that, let's say in a group you are taking a vote or an opinion, if majority people are voting yes, you know that okay fine, this answer probably makes sense. That is why majority voting is used. Now in the GRPO formula, this is the final formula. We are not going to look at this formula at all, and we are not going to understand how it works. But this algorithm which I was talking about, this algorithm is essentially this. Now, here is where the advantages AT comes in. And the way this advantage or algorithm is structured is that you reinforce completions or conversations which have a positive advantage and penalize completions which have a negative advantage. So that is how this algorithm this works. GRPO did not invent this algorithm. It was existing, I would say, from 2000 onwards. People have been making slight changes to it. This is called as the policy gradient algorithm, and PPO did a major change in 2017, after which it became very popular. And after that, GRPO also made a change to this algorithm, but the change was minimal. So the algorithm itself is, there is no innovation there, but how to calculate the advantages, that is something which is very crucial for us. So what we are going to do now is we are going to look at another Google Colab notebook, which you will find by going next to this next notebook and clicking on open with Colab. And we are going to understand a GRPO algorithm properly, so that we are confident when we implement this in a real life project. Okay, all of you, please open this Google Colab notebook. Our objective is to understand the process of reinforcement learning a bit better through this notebook. Please take help of the narration audios and also the AI assistant, which we have curated for every notebooks specifically. So, as I was saying in the beginning of this tutorial, reinforcement learning is a field which is very intuitive to all of us, because it is learning from feedback. If we get a positive feedback, we have to do more of that thing we were doing to get that feedback. If we get a negative feedback, we will do less of that. That is exactly what we are doing here at the heart of it. The only thing is that it is wrapped up in some mathematics, uh, and that's it. But at the heart of it, this is exactly what reinforcement learning is trying to do. In our context, what RL is trying to do is it's trying to give more importance to conversations which have been given higher rewards by our PRM, and give less importance or penalize conversations which have been given negative rewards by our PRM. Okay, so let's start. First, as always, we'll introduce a bit of a theory in this notebook. Okay, so in the previous notebook, we built a system that extracts training samples from the conversations. But how do we actually use this data to improve the model? And we need two things. We need a score, we need a way to score each response. Was the response good? Was it bad? Was it neutral? And we also need a way to update the model so that it produces more good responses and fewer bad responses. And we use a method called GRPO, which is group relative policy optimization, which eliminates the need for a critique network and that reduces compute costs by 50%. This method, as I discussed before, was developed by the DeepSeek team in a landmark paper which came out in 2024. Interestingly, that paper got buried down a little bit after their release called DeepSeek R1 in 2025. But that was the main paper which had introduced GRPO before itself. So in this notebook, we will implement a PRM with majority voting. We will also do a GRPO advantage calculation from scratch. There are two other tricks that we do here. There is a clip higher clipping mechanism. We will not be focusing too much on this, but we will focus on this overlong reward shaping for length control. Some of you might have seen that sometimes LLMs tend to ramble a lot. They tend to give very verbose responses which we want to penalize. This is exactly what this trick does. So there are two simple tricks which are implemented, and we are going to understand that as well. This is an intuition regarding advantages which we have briefly discussed about. Imagine that you are a teacher grading essays and you have four students who have written an essay on the same topic. Student A writes an excellent essay and you give a grade of A plus. Student B wrote a terrible essay, you gave a grade of F here. Student C wrote a good essay, you gave a grade of A, and student D wrote an average essay, so you gave a grade of C. Now, instead of giving absolute grades, you rank them relative to each other. A and C above average, B is below average, and D is slightly above average. So, this is the core idea of GRPO, which is where we rank conversations relative to each other and calculate advantages. A positive advantage means that you are doing better than the average. So A and C have positive advantage, B has a negative advantage, and D has a slightly positive advantage. And to get the initial grade itself, we use a process reward model. Okay, so this is a bit of a mathematics, which is essentially saying the same thing. In the process reward model, we run, let's say, three different evaluations and we choose the majority, whichever answer has been voted the most. And in GRPO, we already saw this is the formula which has been which is used. The only thing which we haven't seen before is this overlong reward shaping, which is quite simple actually. It means that if the conversation length by the LLM increases beyond this capacity, you give a reward of -1, and otherwise you give a reward which increases with the response length. So responses within a safe zone get no penalty, but responses approaching the limit get a linearly increasing penalty. So this is usually done because sometimes LLMs tend to give a very verbose response, which you don't really want. So you want to penalize the LLM if it is giving a response that is unnecessarily very verbose. Okay, so this is how reinforcement learning in GRPO works. And as I said at the start of this tutorial, I want to use this time to help everyone understand the effectiveness of RL and to not shy away from it, even though the formula might look a little bit intense. If you know where to use it and how to use it, you can achieve a lot of interesting projects using reinforcement learning. So first we do our normal setups. Then we write a code for a process reward model with majority voting. Uh, so here in the trial one, we get one, two, three, four, five votes, and the majority is +1. In trial two, the majority is +1, etc. And here there is a graph which shows how majority voting improves the accuracy. So if you look at m equal to 1, which is you just take a single vote, then the accuracy is around 69%. But if you increase the number of majority votes, typically the accuracy tends to rise. This is of course a bit heuristic. This is not a actual trend, but it you can see it saturates after some time if you increase the number of majority votes. In the paper that we looked at, they are choosing m equal to 3, as we saw here. uh, Multiple times it is evaluated 3 times and you take the majority out of the 3. Okay, so this is the process reward model. It is here we have not implemented an actual PRM, but it is just something which is formula based. In an actual PRM, there is a LLM which is used to score the conversations and give values. Now here we are calculating the advantages. You can see the advantage has a very simple formula. You subtract the mean from the rewards and divide the standard deviation. And here we are taking an example, the same example that we took in the uh, in this document. 1 minus 1 1 and 0. And you can see these are the advantages we calculated here. So the same advantages we'll see being calculated here with a slight difference, I think, because the standard deviation used here is 0.96, whereas in the document it was 0.83, I believe. So if you look at how the advantages vary, the raw rewards are blue, which is 1 minus 1 1 and 0. And you can see there is no zero value in the advantages, because negative means that it's performing worse than the baseline. So there are two which have the same positive advantage, and one has a very negative advantage which had a reward of minus 1. So this is one distribution of GRPO advantages just given as a reference. And now afterwards there is a section on overlong reward shaping, where there is a nice graph which I want to show to all of you. So here if you see, from 0 to 800 there is no length penalty, okay, because you have a response which is well within the safe zone. So this green dotted line, this is the safe zone over here. And after that you can see, I'll just take a screenshot of this, I'll put it in the notes. After that you can see that the penalty increases from 0 to negative value, and then after 1000 tokens the penalty remains constant. So this is called as overlong reward shaping, and it usually helps in making sure that your LLM does not give answers which are overly verbose, and you get crisp answers. So here you can clearly see after 1000 tokens you give a penalty of minus 1, and from 800 to thousands it linearly decreases, or increases rather, the magnitude from 0 to minus 1. Then this is the second trick which I discussed, which is clipping. You might have seen in this formula there is an epsilon which I have stayed away from, but that epsilon is the clipping parameter. So they have used a clip higher mechanism which allows the model to make an aggressive update. So this clipping essentially exists because you are saying that even if the reward is very bad, don't tweak the brain that much. If you tweak the brain of a person too much, the person itself might start to say something rubbish. So that's why you don't want to do that. You want to stay slightly conservative, and because of that, people usually have a clipping range. But now here, if you see, if I run this cell, yeah, so this is the clipping cell. If the policy, the clipping value, if the policy ratio becomes more than 1, so this is the policy ratio rho t. If it becomes more than 1.25, which means that you want to make more aggressive updates to the brain, you want to tweak the brain more, you basically clip it. So you say that, okay, I don't want it to behave very bad because the original behavior was decent. If I completely change my model, it's going to perform very randomly. So the analogy is that of a person where the person goes to a neurologist, and the neurologist goes inside the brain and changes the wiring so much that the person that comes out is completely different. You don't want that, that's why you clip it. And usually people clip over here, which is a blue line, but here what they have done is they have clipped a little bit higher, so they allow the policy to change by that much amount, which is something again not a rule as such, but probably they observed that this is giving them better results. So clipping higher essentially means this part. Before, you clipped at this row value, but later you are clipping here, so you're increasing the aggressiveness by this amount. That is what is happening in this. So there are two tricks. One is you penalize longer responses, and second, you allow the model to aggressively change the brain itself. So this is something I think I have also not implemented this, but you can go ahead and implement this. And then there is a Yeah, so this is where you define the loss and you put together in this training loop. Let me see if this, yeah, this runs. So this is the policy model with 46,000 parameters, and if you run this, you will see the training proceed. I have not implemented this clipping, but you can implement all these things together and see the training proceed. Yeah, because this clip loss is not defined, I think this probably might not run. Let's see. Yeah, so this might take some time for you to run, but essentially what here we are asking you to do is define this surrogate loss and then implement these steps on your own. And this will be a good practice for you to implement group relative policy optimization and actually see how it works. Let me quickly go ahead and do this, and I'll get back to this video. Okay, so I have run both of these cells now. Let's see if this training loop runs properly. Yeah, so you can see the training is complete, and the loss is decreasing here, then again increases, and then you can visualize the training results. The GRPO objective, you can see it increases with time, which is what you want. Ideally, you should track the mean rewards also whenever you're running any RL algorithm, because tracking the mean rewards allows you to get a sense of whether you are improving with time or not, because that's one main indicator. So here you can clearly see that there is this upward trend, which is what makes us believe that this objective is being reached slowly with time. And then finally you can visualize this, how the PRM grades it first, then group relative advantages are calculated, then you clip it higher, and finally you get an objective function which increases with time. So this completes our understanding of group relative policy optimization and how it works for a interesting problem statement. This is exactly what we are going to use when we implement our final project, where we tweak the OpenClaw agent and we make it align with our personal preferences. Okay, so now that we have understood the fundamentals completely, we have now completed the fundamentals. In the practicals part, we have added one more layer now. Let me just write it down. The second layer which we have added is how to implement the GRPO RL algorithm. So this was the first notebook and this was the second notebook. The way we have designed this entire notebook and the article is that even if you go through it at your own pace, you will get a sense that you've really understood the subject, which is what I'm trying to demonstrate to you through these examples. Now let me spend a bit of time on the third part, which is the research or the case study in this case. So this is something which we have designed so that several times it happens in the AI field that we understand something theory and then we also implement it for a toy project. But when we get to the real problem statement, suddenly we are not very confident. And this is because of the lack of confidence on implementing algorithms which we fundamentally understand, but we do not have the confidence to deploy those algorithms in real life settings. And many AI companies these days are looking for people who are confident in these skills and apply it to some projects which are real life and not toy data sets. So here what we are going to do is that we are going to look at a actual case study, and I'm going to briefly explain how this case study is structured. But this is, at the end of it, it is like a homework for all of you, because I have implemented these notebooks in front of you, and finally I'm asking you to do this case study afterwards, which includes the same principles that we discussed right now. Okay, so let's understand what this case study is about. In this case study, we are going to be designing and personalizing an enterprise AI coding assistant with conversation based RL. Let's look at the problem statement which has been given to us by the industry. Enterprise developer tools represent a huge billion market which is growing annually. The industry faces a critical challenge. Developers try AI assistants enthusiastically, but they abandon them when the tools fail to adapt to individual workflows. Now, there is a company which is a Series B startup, and it has a flagship product called Code Pilot Enterprise. It is a AI coding assistant that integrates with VS Code, etc. It provides code completion, code review suggestions, test generation, etc. And the underlying model is a fine-tuned 4 billion parameter LLM, which is served on premise. So the current scale is 214 clients, a lot of active developers, etc. Now the business challenge is that they have a developer adoption plateau problem. Despite strong initial sign-up rates, daily active usage has stalled at 34%, and developers start very enthusiastically, but within 2 to 3 weeks, there is a kind of a frustration that develops because the assistant repeatedly makes the same mistakes, and every developer corrects the assistant 8 times per day, which is a big amount. And why it matters is that their competitive advantage depends on developer personalization. Okay, so internal assistant shows that personalized assistant could reduce correction frequency by 60 to 75%, translating to approximately 22 minutes saved by developer per day. Each enterprise client has A100 GPU for model serving. Training must happen on the same hardware without interrupting inference, etc. Let's go ahead and go to the next step. Okay, so the problem is, this is a RL from human feedback problem. Why RL and not SFT? Supervised fine tuning requires curated prompt response pairs, and Nexa code does not have this. What it has is natural conversations where developers have corrected the assistant's mistakes. These corrections are implicit preference signals, not label training example. And RL is the right framework because it can extract training signal from comparative feedback. So the feedback that we have here is comparative, which says that this response is better than that one. Okay, so now what does each training sample consist of? The conversation history up to the assistant's response. This includes previous turns, etc. The response is the assistant's generated response, and the next state signal, the input tuple. So this is very similar to what we are discussing in OpenClaw RL also, but it is formulated as a industry case problem statement. Okay, so the industry has the developers communicating with the AI agent, but the developers are frustrated. So there is a lot of next state signals also where the developers are giving a feedback, and there is a lot of prompt, then the assistant's response and the developer's response, and all of that constitutes training signal. And this personalization can be solved using GRPO, where training a separate critic network is not required. GRPO eliminates the critic. This is the lost function, which we have already looked at in the Google Colab notebook. We use a clipped surrogate with clip higher. We use a reward shaping, which are the two tricks that I had described. Okay, so Now, the next step, we have designed a Google Colab notebook for you, which is provided as a hands on notebook with a lot of to do exercises. So, this is going to take time for you to go through and understand and implement it on your own. But we have given all the setup where to load the data set. So, this is one synthetic data set which we are using, which is the Anthropic HHRLHF dataset, which consists of 1,70,000 plus conversations with chosen and rejected responses. Every conversation has a chosen path, the response the human preferred, and a rejected path, the response that was worse. We will use the human follow up messages as next state signals, just as Nexa Code Systems uses developer constraint correction. So, this is the data set that we will be using, and I think it has already been loaded up for you, so you can load it up. The main uh, the main sections have been divided as to do exercises. For example, parse conversations into training triples, then exploratory data analysis, analyze feedback distribution, prompt injection. We are going to design a process reward model here. You can already see some models have been defined for you. Implement the scoring function, then implement GRPO and actually fine tune the model and see the responses. Evaluate and compare against baseline, and categorize the various failure modes, inference, latency, benchmarking. All of this might sound a little bit challenging for you, but this is the level which all of you have to reach. Once you understand the basics, how reinforcement learning can be used for making assistants aligned with human preferences, this is the notebook which is going to give you the final confidence. So this is the end of the FPR technique, and this is what we want to achieve towards the end. So I expect all of you to go through this notebook, implement it, and you can let us know your results after you have implemented it. Just going back to the main focus of this overall tutorial, we want to build agents which behave according to preferences and learn from conversations. And then we have already covered the F, the P, and the R is something which is given to you in a very structured way and scaffolded way as a homework. So you won't be lost, but you just have to spend time. This is where you will build confidence about applying reinforcement learning to some practical projects. Now, the next part that we are going to do is we are going to actually implement the OpenClaw RL framework, and we are going to integrate it with WhatsApp, and we are going to see a live demo of how it works. This is the platform which I will show all of you right now. Let's just try to see how this works, and I will explain how to build this. But this is what we are going to build. All of the things which we have learned in theory now will give us the confidence to know exactly what happens when we build it in practice. This is the confidence which knowing the concepts from first principles give, which we will demonstrate in the last section of this tutorial. Okay, so far, what we have covered is we have understood our main objective, which is to build a personal AI assistant which behaves according to our preferences. And we want an agent which is continuously improving with time. Now, the way everyone uses OpenClaw is that they connect OpenClaw with some of the communication channels like WhatsApp, Slack, email, etc. And then they use OpenClaw as their personal assistant, which sends the messages on their behalf. Now, as we looked at, OpenClaw has a brain, which is nothing but the LLM itself, which can be Claude, OpenAI, etc. And that brain remains largely fixed. The model is frozen, it doesn't change itself depending on the way the user is having any conversation with the model. And this is exactly what we set out to change in this tutorial. We want to develop a agent which can learn from our conversations continuously without requiring to maybe collect a data set and explicitly fine tune it. That was the whole objective that we started out with. And then at the back of our mind, we knew that we would require reinforcement learning at some stage, because traditionally the method of RL has been the one which is employed for aligning these models towards human preferences. After that, we discussed about the four components of how to integrate reinforcement learning in OpenClaw, or rather, with the broader objective of how to align the agents to behave according to our preferences. The first thing that we observed is that currently OpenClaw, the way it uses the brain is that the brain is locked in a glass door somewhere on some server, and you cannot tweak the brain itself because you do not have the keys to that door. Now, in order to tweak the brain, you need to have keys to the door and you need to have access to it. That is why we need to host it on our own infrastructure. That is the first component, which is the agent that improves itself with time and with the data from the conversations which we are having with the agent. So that is the first component, and this is where our thinking started to diverge from the way 99% of the population is currently using OpenClaw. They are not thinking of serving different models on their own infra and then fine tuning that models. Next, what we looked at was we looked at what is the meaning of a rollout collection. Uh, you have thousands of conversations daily, let's say, with your communication channels, with WhatsApp, with Slack, with email, etc. And you need a pipeline which can gather these conversations, not just gather the conversations, gather the most relevant conversations. So we looked at two types of conversations, one which is called as side turns, which is not important, and main turns. This is where you are interacting with the assistant and giving feedback that this is, I like this, I don't like this, etc. And you want to create a data set at the end of it, where the first data attribute is the conversations, which is the main turns, which is the answer, the assistant's answer, and then your response to it, which implicitly contains your feedback. Now, to design this data set, we have only discussed about the first column, which contains the conversations. But what about the second column, where you are actually scoring these conversations? The way the field started with these scores traditionally is that human labelers used to sit down and write down scores for all these outputs from the model. But since we do not have human labelers, we are going to rely on another separate model to score these conversations, which is called as process reward models. The process reward model is like a judge. What the judge does is that, imagine you are sitting in a room, there is one more person, which is your AI assistant, which is the agent, and then the agent is interacting with you. There is a third person now in the room. There are three people in the room. Let us see if there is any icon for person. Okay, so let's say this is you, this is your agent, and this is the judge. Okay, so this is you, this is your agent, and this is the judge. So there are three people sitting in the room. You and agent are continuously having conversations, and the judge is looking at these conversations and rating them. So there are three people sitting in a room, where the judge is the process reward model, which is looking at the conversations and assigning scores to every conversation. If the conversation is good, by good I mean if the user is satisfied with the agent, then the judge is happy. The judge gives a thumbs up. The judge gives a positive reward. If the user is not satisfied with the agent, then the judge is unhappy, and the judge gives a negative reward. So this is the third component, and finally we have the training. Now this is the most important step. Since we have access to the glass door now, where the brain is located, we can use the keys, and we can open the door and we can actually tweak the brain. But the question is, how do you tweak the brain? How do you exactly change the brain wirings? And this is where we discussed about an algorithm which is called as GRPO, where every reward signal is converted to advantages without requiring a separate critic model. And then it's a very efficient algorithm of wiring your brain. I've discussed the basics, and we also implemented a practical notebook where we saw how GRPO works in practice. In fact, we had two practical notebook implementations. And then finally, we implemented a case study where we looked at how to implement all these learnings in a practical scenario. Now, finally, let us go ahead and look at the last aspect. Remember, we started out this whole conversation by saying that we are going to look at four aspects, and we have basically completed this. And this is what we are going to focus on right now. We are going to deploy it end to end on our own servers, and we are going to understand how OpenClaw improves with time. Okay, now that you have spent time up until this part, let us go ahead and understand something which is very practical and extremely interesting. So, this all that we have covered so far has been a build up to what we are going to look at in the finale or the last part of this tutorial. So, I have created this document which I'm going to briefly go through, which is a complete setup guide of OpenClaw with RL. I have hosted this document on pods.visuara.ai. This is the website, and all of you can basically log in. And I have hosted this for free. You can look at this end-to-end deployment guide so that you can follow it. Okay, so let's now go to the end-to-end deployment. Okay, end-to-end deployment, and let me make the font consistent. Okay, fine. So this is what we are going to look at now. We are going to understand the end-to-end deployment process for building our own personalized assistant which behaves according to our inputs. Okay, so let's go ahead and let's get started. So we want to train an LLM from our own conversations using reinforcement learning. And broadly speaking, we'll be using RunPod. RunPod is a service which lets you rent GPUs, uh, and then it allows you to host models on these rented GPUs. And we are going to use four H100 8 GB GPUs for this purpose. It is going to involve some cost. I will give an analysis of how much cost will be involved. The reason the cost is involved here is because you are using runpod services to host the model and also fine tune it based on your conversation. So there is a lot of requests which are hitting your server, and some computations are happening, and you're getting the responses back from the server. So all of these computations, they have some inherent cost or price attached to it. Okay, so this also gives us an opportunity to discuss how reinforcement learning algorithms are implemented in a scale setting. Whenever there is a scale involved, how do big companies implement RL? And I'm going to make it very simple for everyone so that it doesn't feel very overwhelming, because there is a final objective attached to it. We want to build a platform which looks like this, which understands our conversations from WhatsApp and then scores it. I've deliberately not focused too much on this platform, but we are going to look at it in complete detail as we go along. Okay, so let's go ahead. Okay, so let's look at component by component, and we will try to understand the architecture again, sort of like a revision, and this time we'll give proper names to the models that we are using. So we are using a quen 3 4.4 billion parameter model. So let's the agent, which was the brain. Here we are going to use a quen model as our agent. So this is the this font is hideous. Okay, so this is the quen model, and we are going to be using quen 3 4 billion parameter model. Okay, so this is our brain, and this is basically where all the intelligence is coming from, and we want to tweak this brain based on the conversations that we are having with it. So this is the component number one, which is the agent, and the question is, where is this agent hosted on? The agent is hosted on GPUs on RunPod. Now, for people who have not heard of RunPod before, it is a very convenient way of renting out GPUs. So you just go ahead to runpod.io and you create an account, and you will see an interface where it's very easy to purchase runpod. So for example, this is my interface currently, but let's say I want to purchase some runpods. I click on deploy, and these are the runpods that we are going to use, H100s. And then I will discuss how to configure the settings, etc. But basically the main point is that the GPUs will be hosted on runpod, and this is where all these 4 billion parameter model will be residing. Okay, so this is the first component, which is the agent itself, and it will be running on the runpod GPUs. Now let's look at the other components. The second component that we have been discussing about is the rollout collector. And let's type it here, rollout collector. And I'm going to increase the, okay, so the font size so that it's visible. Okay, so the rollout collector is the next component, and this is where we are going to use something which is industry level. We are going to use a framework which allows us to seamlessly collect these rollouts. Okay, so the next part in our pipeline is the rollout collector. The first part, which we have already discussed, is the agent, which is hosted on the runpod, and which is the quen 3 4 billion parameter model. Now, the next component, which is the rollout collector. What is the purpose of the rollout collector? Let's try to understand that. The purpose of the rollout collector is firstly to query the agent. Okay, so the purpose of the rollout collector is to query the agent. So this queries the agent, and after the agent is queried, you get responses back from the agent. Okay, so let's say you are chatting with the agent through WhatsApp, and you are asking a bunch of questions to your agent, and you are getting responses back from the agent. This is a typical workflow which everyone who uses OpenClaw follows. Now, whenever you ask something, what is happening is that your request is being taken and transferred to the LLM, and it is hitting the server, and you get the response back from the server. Now, the same process is going to work for our workflow also. The only difference is that here the agent is hosted on our own GPUs, which we have rented. Okay, so the queries are going to the agent and the response is coming back from the agent. So the purpose of the rollout collector is to make sure that the responses which the agent is giving is fast. Typically, in companies like Anthropic, OpenAI, the inference speed is very low, which means that you get your answers very fast. And we don't think of the inference process that much, but there is a very complex architecture which is going on inside these LLMs. When your query is passed to the LLM, the query internally goes through a lot of building blocks, and there is a lot of computations which is performed, and finally you get your answer back. Now, all of this happens in seconds or even milliseconds, because the answer you get when you query ChatGPT is literally 1 or 2 seconds. Now, since we are using our own infrastructure to serve these models, we have to take care of the inference pipeline on our own. This is what the rollout collector does. So, the rollout collector, we will just mark it over here that it takes care of inference. What does inference mean? Inference simply means that you are querying the model and you are getting the response back from the model. That's it. But it has to happen super fast. So you need a separate framework for that. And the framework that we are going to be using is called as SGLang. So let's look at this GitHub repo for SGLang. You can see that it is quite popular. It has 24K stars. For people who are only doing toy projects, they will not be aware of this framework at all. But since we are looking at an industry level project, we have to learn about this framework. So let's look at this section where it says SGLang is a high performance serving framework for LLMs, and it provides a very fast runtime. It is designed to deliver low latency and high throughput inference. That is the main purpose of SGLang. So let me add this in my notes so that all of us can refer to it later as well. Okay, so this is the main purpose of SGLang, and we are going to be using SGLang framework as the rollout collector. Now let us move to the third component, which is the PRM, the process reward model. So let me build out another block for this. So this is the process reward model. And what does the process reward model do? The process reward model looks at your conversations and provides a score to those conversations. So this is also some kind of inferencing going on here, because the rollout collector is linked to the agent, that is fine, but the process reward model is linked to the rollout collector. Why is it linked to the rollout collector? Because it is looking at the rollouts and it is scoring every single rollout, and that is also going to take time, right? Because you are looking at the rollouts, and then you have a system prompt, you have a specific way of judging those rollouts. We discussed about the three people sitting in the room, right? This is what the judge is doing. The judge is looking at the rollouts and the judge is giving scores to the rollouts. So I am the judge, I am the process reward model, and to give the scores very fast, I need an engine which allows me to do that. And here also we are going to be using SGLang to basically deliver the scores in a way that is very fast and efficient. Okay, so we have looked at the rollout component and the PRM, which is the process reward model component as well. Now let's look at something which is the last component, that is the training component. Our fourth component, as we have discussed, is the actual training, which means that the data set that we have built, the conversations and the scores, someone has to actually go ahead and do the training, right? Someone has to modify the weights of the Quen model. Someone has to run backward propagation. Someone has to run gradient descent. All of these steps have to be carried out in a very efficient manner. Now, the interesting thing is that we cannot use the same framework for training as well. And the reason is the training inference should not wait while we are training. Both these components should be going on parallelly at the same time. If you use the same framework, then what will happen is that we collect a lot of conversations, then we wait for the training. And if, let's say, I am the user, I want to have conversations with my agent, for a long time I will not get any response back from the agent. And the reason is that the framework is so busy training that we do not have any compute for inference left. That is why we use a different framework for training, which is called as Megatron LM. And this is a framework which we will be using for doing our training. Let us look at the Megatron framework in detail. So the Megatron LM is a framework which is used to train transformer model. It is developed by NVIDIA. Let me take a screenshot about this framework, and we will put it in our notes. Okay, so far we have looked at SGLang, which is used for inferencing. It is used for component 2 and component 3. Component 4 uses Megatron, which is a library for custom training frameworks, which is extremely optimized. So the training is going to happen very fast because of this Megatron LM framework. Whenever you are using reinforcement learning, you have to use different frameworks because there are different components which are implicitly involved. Now, the question that might come to your mind is, okay, fine, I have these four components, and the first component is the agent, which is hosted on the GPU itself. The second component is the rollout collector, which is linked with the agent, that is using SGLang. The third component is linked with the second component, and that is also using SGLang. And the final component is using Megatron LM. So imagine that you have a classroom where every student has a specific role. Someone is good at debating, someone is good at math, someone is good at science. All of them have a specific role. But if you want to get something done out of the class, a project, let's say, you have to have someone like a class monitor who is orchestrating all of these people so that the job is done. Similarly, we have an orchestrator for our framework, which is called as Ray. And here we are calling it Ray plus line, but the main architecture or the main orchestrator that we are going to be using is called as the Ray framework. Now this has become an industry standard for reinforcement learning because it allows you to manage different manage any workflow where there are a lot of different components involved. So you can see here it has almost 40,000 stars. It's an AI compute engine which consists of a core distributed runtime. Let us look at what Ray actually does. Okay, so Ray is a unified framework for scaling AI applications. It consists of a distributed runtime and a set of libraries. So you can define your LLMs, you can define your components within the Ray itself. Okay, so Ray is something which, let's say in the class, we have these four students, right, who are good at four different roles. Ray is something who is going to divide these groups separately and assign separate jobs to them. So let us draw an image of a classroom, and let us say that we have different components here, right? We have an agent component who is which is the LLM serving the responses. We have the rollout component, we have the PRM component, and then we have the actual training component also. So the place which accumulates all of these components together is called Ray. In any reinforcement learning framework which you see, there are going to be multiple components. As we saw in PPO, we had a critique model, so that was an additional model on top of all these models. So you would have had to allocate an additional block in your architecture. Now, still we are not done here because Ray just allocates memory to different components. It doesn't tell you when to do what. For example, I have a very specific logic, right? That after 32 conversations of my user with my agent, I need to log those 32 conversations in a specific format. I need to put it to my process reward model, score it, and then I have to train my model or fine tune my model after every 32 conversations. Where is all this logic written? And to understand that, we are going to look at another framework which is called as Slime. So Slime is a LLM post-training framework which is specifically designed to scale reinforcement learning. And that is why here you see the framework being written as Ray plus Slime. So we are using these two different frameworks, which is like an orchestrator block that connects all of these students together and gets the work done out of them. So let me copy and paste this because this is something which has to be there in our notes. Okay, so just to summarize, we have four components. The agent is hosted on our run pod, which is the Quen 4 billion parameter model. We have the PRM, which is the process reward model, and the rollout collector. The rollout collector is collecting all the responses from the LLM. So it needs to be very fast, and we need to use an inference engine for it. That is why we use SGLang, and we use the same engine for the process reward model scoring as well. And then for the training itself, we use a framework called Megatron LM. All of these are students who are good at their specific roles, but to connect all of them together, we use the Ray framework, and to get the work done from them, we use the Slime framework. These are all the frameworks that we are going to use in our architecture. It sounds a little bit complex, but when we run it, we'll see that it is extremely effective, and we will be able to run complex architectures in reinforcement learning with this same setup replicated for different objectives. So in this specific project, we are going to use four H100 GPUs. Out of this, we are going to allocate two to the actor. We are going to allocate one to the rollout and one to the PRM. Okay, so this is how we are going to allocate the GPUs. Why maximum have been allocated to the actor? Because we have to train the actor every 32 conversations. So there is a lot of computing power that goes into fine tuning. Whereas rollout and PRM are not that intensive. Rollout is simply generating 32 or a lot of conversations one at a time. And PRM is something which is grading your conversation. So you don't need a lot of GPUs for the rollout and the PRM. Okay, so to implement this project end to end, this is what you will need. The first is access to H100 GPUs, which is over here. If you see, these GPUs are available on the run pod, where you just have to select the number of GPUs here, and then you need a Hugging Face account, which is free. Everyone can download these weights. You need a local machine, that's fine. And the total cost for this 3 to 4 hour session where the agent will be improving through our conversations is $30 to $45. Now in this guide, I have also linked a GitHub repo, which is over here. And in this GitHub repo, I have created very simple scripts for everyone, where you can, very detailed instructions have been given over here to how to generate a dashboard which looks like this. It really looks very beautiful, but it is going to take implementation of all these steps. I have written everything in a very proper manner so that all of you can replicate it very easily. Okay, now that we have understood how the four components actually work and the frameworks that we are going to use for these four components, let us understand how we can implement this on our own. And I will walk you through all the steps in detail. The first step is to create a run pod account and to create a new pod with these settings. Now, When you go to run pod, you will see an option which looks like this. There is an option here of edit. Okay. Now here, this is where you have to enter this container details, which is slimerl/slime latest. Now the reason this is important is because this is something which pulls everything and downloads all the dependencies for you. You don't have to do much, since it is the container image, so it has all the dependencies pre-installed. Initially I tried doing pip install for every single component, and it was breaking. Now you have to set up a start command here, which is bash sleep infinity. That is something you can do in start command here. Okay. And you have to increase the container disk size to 150 GB. And here you have to expose three HTTP ports here. And then when you do that, just click on set overrides. And when you click on deploy pod, it will take some time for the pod to actually connect. Now this is the pod which I am currently running for this exact same setup, and you can see this is how it should look like finally. I have exposed three ports: 8082, 8265, and 30,000. So we can actually see how the ray dashboard looks like. This is the ray dashboard where it is coordinating all these jobs simultaneously, and there are other ports which have been exposed. Okay. So now, once we have understood this, you can SSH into your pod, which allows you to, you can directly work from your terminal. Actually, you don't need to open VS Code. You can simply do this SSH operation, which means it will allow you to control the remote server from your own terminal. Now, what you have to do as the first step is you just have to run this script bash setup.sh. This will verify whether you have these GPUs and the correct image. It will clone the repository. It will download the model for you, and it will create checkpoints and directories. So you just have to run one single script, and it will create all the required details for you. Now, after this is created, next step is the very important step, because this is where we will be actually launching the training pipeline. Some of you might be thinking, where are we connecting OpenClaw here? Isn't that what we should do first? That is very straightforward. First, what you need to do is you need to deploy all these models on your infrastructure, and get the infrastructure working. It is similar to in the house when you go and start living in your house. If the plumbing is not working, then would you be able to live peacefully in the house? Similarly, right now we are taking care of the plumbing aspect. After that, we'll be easily connecting OpenClaw with it. So next, you have to download this deploy script, and then you just have to launch this server. What this will do is it will start the full training pipeline. Now, after the training pipeline it started, it should look something like this. So you see, this is where I had given the command initially, the same file I'm running, and it takes 3 to 5 minutes, and finally you should get something which looks like this. This is where you will see all this. You see here SGLang engine, rollout manager. All of this now we have, since we have discussed in theory, we'll be able to understand what all these different things are doing. For example, rollout manager is collecting the conversations, and it is using the SGLang engine to do that. Okay, so this is what should be the output after the server is launched. And then you can also deploy this second bash script, which allows you to do a health check, list all the models, etc. Once you set up the server and the training pipeline is working, this means that we start all the components: the Ray cluster, SGLang inference, PRM scoring, and the Megatron LM training. And it feels very satisfying once everything is running, because this means that the plumbing actually works. You have set up an infrastructure where all these components are working together very seamlessly, and you will be finally ready to implement reinforcement learning for your project. Okay, next what you can do is, without focusing on OpenClaw, first we can just chat with our model, because OpenClaw is just an agent which is sitting on our WhatsApp. That is like a fancy application. You can simply interact through chat and let the brain improve according to your preferences. Okay, that is the first proof of concept that our fine tuning has actually worked before even going to OpenClaw. Because if the chatting works, then the OpenClaw implementation is definitely going to work. So what we have done here is, first we do the setup, which downloads the model from Hugging Face and sets up the Docker container, etc. After the setup, you start the training server. This will make sure that all the components are working seamlessly. And then you first chat with Quen. Although this interface is a bit cumbersome because there are two terminals open. There is one terminal here where you will see what the PRM is scoring, and then the second terminal is the chat window. So initially I also tried doing that, but that's where it becomes difficult to keep track of both the terminals at the same time. Okay, so you can start chatting, and then you can understand the PRM. You can actually see the process reward model scoring, and you can see three votes, and you can see it taking the majority of the votes also. And here I have given some steps where you can actually monitor the training, and you can run before and after benchmarks to see if our brain is actually improving, because we are tweaking our brain. We want it to behave according to what we want, but we need to have some benchmarks to make sure that whether the tweaking is actually working or not. So that is why we have given these steps 9 and step 10. The next part, which is the most interesting part, is the dashboard setup. The reason I thought about this is because it's very cumbersome to open two terminals where on one terminal you are chatting and on the second terminal you are seeing the process reward model. Instead, it would be great if there is one single dashboard where you can see everything. So you can open up a second terminal on the pod, and then you can just type this, uh, which will actually start the metric server. It is not yet deployed. It will just start the server, which collects all the information from uh, the engines which you are running. And then after that, you have to go to your local machine, because that is where you will be seeing the dashboard. And you have to just follow these steps over here and run the dashboard. After you run the dashboard, you will actually see something which looks like this. Now, you see this interface is very beautiful. It has a lot of things going on here. On the right are the chats which you are having, and on the left you can actually see four panels. The first is the batch progress, which is the 32 conversations which are collected together. And for all these 32 conversations, you can see the PRM score trend. You can see the reward model and the reward which the model gives for every single conversation. Remember, this is the same conversation which we had implemented in Google Colab Notebook, where it was extracting the main turns from the conversation, and now we are scoring these turns using the process reward model. And you can also see the GPU utilization over here. Now, initially, without even connecting to WhatsApp, you will get or OpenClaw, you will get just a chat window, and that is like a first proof of concept that it works. I have connected here with my OpenClaw. I'm going to demonstrate that in a second. But before that, this is the interface, and you can actually see all these GPUs working in a very nice way. For example, if you give a conversation, you will see GPU 2 load up. Why is GPU 2 loading up? Because uh, the rollout collection engine is working, and you get a response back from the LLM. After that, when the response comes from the LLM and you interact with it, you will see GPU 3 also load up. because it scores your feedback to the LLM. GPU 0 and 1, remember, are associated only with the actor. So if you go here and if you see GPU 0 and 1, the first two GPUs are only associated with the actor. So they will be loaded only after 32 conversations are done. They will be used only after 32 conversations are done. So you can see that also in the dashboard. You can see the GPU utilization, how it changes from one GPU to another. I will show that in a second, how that change actually works. And the last part, which is what this tutorial is all about, is connecting OpenClaw. Now that is straightforward because we already have tested everything and our framework works for chatting. WhatsApp is just another means to chat. So first you have to install OpenClaw, where I have given the instructions over here, and you have to configure the provider. For example, OpenClaw by default connects to some LLMs like Claude or OpenAI, but here you have to give your pod base URL, and you have to give the name of the model as well, and the name here is SGLang. SGLang Qwen 4 billion parameter model. And here you use the same API key you set in step 5, which is, I think, this one. Yeah, this is, so you can pick any key over here and you can use that same key in the OpenClaw configurator. Then you can simply write OpenClaw pair. It will ask you to scan the QR code and connect with your WhatsApp. And you can just then OpenClaw gateway and then just start the gateway. Now, once that is done and your OpenClaw is connected to your engine, this is what I have done. I'll be demonstrating it right now. So here, let's say I write, uh, how does, or what is a transformer architecture in AI. So it has registered my message, and hopefully I will get a response back from OpenClaw, which is the agent that is connected to my WhatsApp. And yeah, you see, I get a response back over here from OpenClaw, where it says here the exact phrase you can use right now with your students, transformer architecture. And then the same I can see reflected over here. Okay, now you can just say that I did not like this explanation. It is not given from first principles. Please do not use emojis and keep it very crisp and clear. So this is the feedback which you have given, which is a negative feedback, right? And now let's see what happens. So it says now it has given one brief description, made it very crisp and clear. Now because your feedback was negative, you see it gives a score of 0 here. And this is exactly what we want, right? Because your conversations are graded based on your feedback. Now you say that, excellent, this is exactly what I wanted, but it is still too short. Can you just increase the length a little bit? So now let's see which GPUs are loaded up. Okay, so when I have given the input, you should see ideally GPU 2 load up and then transfer to GPU 3. So now, because I said excellent, you can see the PRM has given a score of +1, which means that this PRM trend is actually working, and I'm proceeding. I'm on batch 6 now compared to batch 32. And what I can do is, because I am transferring quickly, I'll open my phone and I will type a message. So you will probably see the GPU 2 and 3 load up. So now I'll say, now give me explanation for CNN. Just keep observing the GPU 2 and GPU 3 tabs. So you see here 89%. This is your rollout collector, and GPU 3 is your PRM. So you see how it transfers from GPU 2 to GPU 3, again goes back to 0 quickly. And it has actually learned from my feedback before, and it is now starting to give me something which is very crisp. This is before fine tuning, but after you do it 32 times, the result is even better. So once this batch progresses 32 times, it will reset, it will change the weights, and there you will see GPU 0 and GPU 1 being activated. And then this process will continue. And this is a proof that your agent is actually understanding your behavior, scoring it, and fine tuning itself based on your preferences. All of this is very easy to implement. You just need a small budget to start out with. And once you do that, the implementation gives a lot of satisfaction. Also, it creates a lot of open avenues for trying out different algorithms and strategies. So here I have specifically instructed, for example, if you see here, the way the reward models is trained. So I would have written this somewhere over here. Yeah, the way it is trained is I have added explicit user sentiment which overrides the LLM based PRM, which means that if sometimes what happens is that the LLM fails to detect your intent, whether you have given a positive or negative feedback. So I have modified the reward model scoring a little bit to make sure that it actually takes into account user feedback properly. Okay, so this brings me to the end of the tutorial. I really hope it provided a lot of value to you, and it also helped you understand a bit about reinforcement learning GRPO. It allowed me to explain GRPO and RL because it is linked to an application which is very practical. And finally, when all of you see this dashboard, it feels very satisfying. So there is a final outcome which is attached to this project, which gives a lot of satisfaction. Thank you very much, everyone. And I hope you go to the Pods website, which is where all the details, the article, the Google Colab notebooks, the narration, the chatbot, and the GitHub repo PDF, everything is hosted in pods.visual.ai. And you can feel free to check out other content also. The way I taught right now in this lecture, it is the exact same way we are teaching every single concept in Pods. So it is a platform which we have curated with a lot of care, and I hope all of you find a lot of value here. Thank you, everyone. Bye.